only 18 participants are here. Let's wait for a couple more minutes. I think more participants can come. Okay, good afternoon to everyone. 20 participants has come now. Let's wait for 5 minutes, irrespective of whether they are coming or not. Start the class. Okay, we'll start the class today. Okay, so today what we are going to see is mutation. Okay, so what is mutation? Mutation was to be discovered by the Hugo Duelis. So that means any sudden heritable change. So how this sudden heritable change comes? This sudden heritable change may be occurring naturally. So that may be natural mutation or it may be induced mutation sometimes. If we are putting some chemicals or something, that means we are getting the induced mutation. So that may be of two types, and maybe it may be occurring naturally or it may be induced with the help of some of the chemical agents. Okay. So that is what these mutations will do. So what is the thing is they will do something with the nucleotide sequences. It is they will change the nucleotide or the base sequences of DNA. We all know that the nucleotide that we are having the 4 nucleotides as in the case of the DNA. Having the 4 nucleotides as in the case of the DNA. Okay, adenine, guanine, cytosine, and thymine. We are having uracil as in the case of the RNA. That's all we know. So if there is some changes to be happening on that sequences, we can call it as the mutation. Okay, so this mutation, in this class we are going to see about mainly the 2 mutations. One is the chemical, how the chemicals are to be inducing the mutations, or how the radiations, that is the X-rays, UV rays, gamma rays, and how they are to be doing the mutation. Okay. So as in the case of everyone, mutation is happening everywhere, with everyone, with the bacteria, with the humans, and everything. Don't think every mutation has to be lethal, or every mutation should be giving you some entirely different result. That is, sometimes it may change the coding sequences for new amino acids in proteins or not. Sometimes they may you may observe some changes in the DNA sequences that will be reflected in the protein nature. That is it's related in the it will be reflected in amino acid sequences that in turn may give you some newer proteins. But sometimes it will not be having any effect. We are having the first important mutation is the point mutation. So what is the very important thing as in the case of the point mutation is, the first example is we are having the no mutation. Second example is the silent mutation. So silent mutation means I will just want to go to first to show you this. This is a genetic code. So you can see all the genetic code is it's a triplet code. So I will take the first example and I will tell you about the silent mutation. So if you here in the silent mutation for the phenylalanine, we are having the uracil 3 triplet of uracil or doublet of uracil plus cytosine. Okay. So here in this case, this U is replaced by C. We are having the same phenylalanine. That is, some mutation is taking place, but it is not having any change. Okay. Second, I will go to the next example of leucine. or I will go to the this example of alanine and methionine. So here you can see AUU will code for the alanine and AUG will code for methionine. So there is a small sequence change of U to G. So as a result, the entire thing has been changed. So it has been, the alanine has been converted to the methionine. Yeah, it is only converted to methionine. So this is a missense mutation. Missense mutation. So there is another one more mutation is that is called a nonsense mutation. So this type of mutations may reflect on the protein or may not reflect on the protein. However, there is that type that is called as a nonsense mutation. Nonsense means it make something without any sense. You can see here, UAA will code for tyrosine. However, UAA will code for the stop signals. That means if the gene sequence is getting the UAA, will immediately terminate the protein synthesis. So this is very dangerous. Okay, now we will go to the thing. So you are having all the three mutations. I show you the silent mutation. Both of them will code for the same reason. However, this is a nonsense mutation. A simple change may give you a stop, and we are also having the missense mutation. So that is also again divided into the conservative and the non-conservative region. So what is the difference between the conservative and non-conservative is that if the changes is taking place in the polar region, we call it a non-conservative. Otherwise, we are calling it as the conservative one. We are going for the point mutation. So the point mutation means the substitution of one base. So many things may happen. Just think about your team of players. You can do something. First is what you can do is you can substitute. Suppose five players are playing. You can ask one player to come out and you can replace it with another player. That is one more one change. Second change is deletion or addition. So sometimes what it will do, you may remove sometimes due to some fouls or something, they may remove a player. Okay. The third thing is sometimes if you want your team to be strong, you are putting another additional member. Some matches, but you are putting an additional member. That is the addition of a single base. Next one is suppose if you are seeing that your players are not performing well, you are removing a certain set of players out and you are replacing it with another set of players. So that is the deletion or addition of a small number. It may reflect the addition or addition of small number of bases. That is from here onward until now what we have been seeing, we will be removing or changing only a single base, but it is here we are to be doing it for more than one basis. Right? And again the thing is these substitutions, as in the case of the point mutation, where they will go. There is two types of substitutions. One is transition, next one is the transversion. So what is the difference between the transition and the transversion? We all know that there are two base pairs. One is purine or pyrimidine. So if some substitution is taking place within the purine itself or within the pyrimidine itself, we can call it as the transition substitution. However, if the substitution is taking place outside purine, that is a purine with a pyrimidine or a pyrimidine with a purine, you can call it as a transverse substitution. I am repeating one more time. So we are having two things. Purine means adenine and guanine are purine, pyrimidine are thiamine and cytosine are pyrimidine. So if the substitution is taking place within purine or within pyrimidine, we can call it as a transition substitution. However, if some change is taking place, suppose if change is taking place between purine and pyrimidine or between pyrimidine and purine, we can call it as a transversion substitution. Okay. So you can see it here. So I already told you that adenine and guanine. purine and cytosine kinase. So you can see transition is uh, the same between the same group, either purine pyrimidine to pyrimidine or purine to purine. However, as because of the transversion, this pyrimidine is converted to purine or purine is converted to pyrimidine. You can see it over here. So alternatively, the change is to be here. So here the transition mutation, it is exactly it is taking AT to GC. So within the same group, they are to be taking the purine to purine or pyrimidine to pyrimidine. However, here let's see the transversion by which the change is taken from pyrimidine to purine. It's a result of point mutation we already see. So I think silent mutation means they want to code for different objects. So there is no change over here. There is no change. So that is called as a silent mutation. Missense mutation means you change an amino acid. You can see here. You can see a change in the amino acid. But that change in the amino acid may not reflect in the functional. So even though there is a small change in the amino acid, there won't be that will not be reflected in the function and the quality of the protein. Next one is a nonsense protein. That is I will talk to you. That will order some of the stop codons. So the stop codons mean they will immediately terminate the protein. That's a bit dangerous one. Okay, so we'll see. So this is the silent mutation. Okay, no change in amino acid. So different triplets are to be coding for same amino acid. There is a redundancy and duplication is identical. No change in amino acid is to be produced. Missense produces change in the amino acid sequence in the protein. So that is the histidine seen for the enzyme. So that is already told you a small change in the amino acid that may or may not reflect the function of the protein. So nonsense protein means they will completely stop the protein synthesis. Okay, so we can see about to the that is I already told you the point in actually the chromosomal mutation. The frame shift mutation we can also call it. So they are more extensive. So more extensive means they are more elaborated. That is a very small because it includes only a small nucleotide or a set of nucleotides. But here the change is up to a part of the whole protein. So what are the different things that may occur? That may occur is a deletion. First thing is deletion. Some sequence may be deleted. Duplications may be done. Some of the sequences may be repeated. Inversion, some sequences were to be added, but unfortunately in the opposite order. And some translocations will also be done. That is moved from one segment to the other. We will see what are the different things. Okay, first is the deletion. So what it will do? Deletion is automatically it will not be very fatal. In some cases, only it will be very fatal. Otherwise, the DNA polymerase can repair the small strand missing sequences. However, here you can see a lot of sequences has been lost. So that it may be very fatal. One good example is the triad syndrome. So that is a large deletion of the chromosome 5 in the human. So what it will do is the newly born babies will start to cry like in the voice of cat. So it is called by the name of triad syndrome. And so basically this is a big issue. So actually what they will do is they will take the pictures, the eye pictures of that is found with the cats. So that is another chromosomal disorder. Next one is the duplication. Okay, so it will depend upon where the region is to be duplicated. So we are having two regions basically. One is a coding region, and the next Next one is a non-coding region. So something if it is done in the coding region, it will definitely be a problem. However, if something is to be taking place in the non-coding region, means it won't be creating much of the issues over there. So with the duplications, it should be carefully observed where it is to be exactly happening. Next one is the inversion. Inversion is nothing but the rearrangement. So rearrangement, you can see the entire thing is to be rearranged. So you can see the rearrangement here. You can A, B, C, D, E, F. So you can see this region is to be inverted and it's to be rearranged. So that is B, C, D. See it in the order. B, B, C, D. So that is to be inverted. This particular region is to be inverted. So here this inversion will not create much abnormalities. However, if these inversions are to be attached with some extra regions of DNA, then there may be some abnormal changes in the behavior of the genes that is to be concerning with the particular chromosome. Next one is the base analog. Base analogs are nothing, and now we are going to see what is the chemical mutation. Chemical mutation, we are having the base analog. Base analog. Analog means something that is similar. Bases, we are having the four bases: adenine, guanine, cytosine, and threonine. So we are having some chemicals that is having the structural similarity with that of one of the bases. So we can call them as a base analog. So, however, what is the problem with it? Okay, let it have a different problem. The problem is their base pairing properties will be different. So automatically we all know that adenine will pair with thymine, cytosine will pair with guanine. This thing may differ if one base analog is to be incorporating into the growing DNA chain. Okay. The very common base analog is the 5-bromo uracil. It is an analog to thymine. That is has the structure that is not similar to that of the thymine. However, the biggest issue is that its base pairing properties will not be similar as that of the thymine. Okay, so again, what you can see is the presence of bromo substituent allow the base to mispair with guanine. So we all know that thymine means it has to mispair with Jivita. Kindly mute your. So I am talking about the base analogs. So the thing is, I'm talking about the 5-bromo uracil. This 5-bromo uracil, is having the property as that of the thymine. So what it has to do? It has to pair with adenine. However, it is having a bromo substituent. So this bromo substituent will cause it to mispair. So what it will do? It will pair with guanine. Suppose guanine is has to pair with cytosine. However, here in this case, thymine is pairing with guanine. So as a result, it is leading to the mutation. So you can see it over here. So we are having the thymine, adenine. So we are having the 5-bromouracil, which is an analog to the thymine. So that is having some similar structure that of the thymine. So it is since it is having a similar structure, it is going on for the base pair. So when it is going on for the replication, the first one pair is not having any issues. However, you can see in the second base pairing, we are having a cytosine to guanine. So here we need to have adenine to thymine or thymine to adenine over here. However, we are getting a new base pairing, that is cytosine to guanine. That is, in this base pairing, we don't have a cytosine to guanine. However, due to the base mispairing with that of the analog, we are getting the cytosine to guanine. Next one is alkylating agents. So again, it is not, but we are having the bases, adenine, cytosine, guanine. So what we will do is, if we are adding a nitrogen group, either to the nitrogen in the seventh position of guanine, or to the adenine in the third position. Okay, so it will lead to some changes. So what are the changes? It will lead to the alkylation, possibility of ionization is increased. So it will lead to the ionization. So if you are adding some alkylate will lead to the possibility of increased ionization. So when there is increased ionization, there is a chance for the base pairing errors. So that means we will not be getting the right bases. Okay. Again, what it will do is, so this hydrolysis of linkage between the base sugars. So there may be, due to this hydrolysis, there may be some gap in the chain. That is when DNA base pair is to be lost. So if one is to be lost, what it may do is, sometimes there may be, we may get a correct base pair. Okay. Sometimes that is we will be getting a correct base pair. However, if we are not getting a correct base pair, that may lead to the mutation. So the phenomenon of the loss of the alkylated bases of the DNA, the breaking of the bond or joining the DNA is called mutation. That is the loss of alkylated bases. So what we will do is, with this mispairing, what it will do is, the loss of the DNA molecule will be there, and sometimes the gap will be repaired by the DNA molecule. However, if in some cases it may not be repaired, so in that case, there is a two chances. That is, one chance is maybe the correct base pair may come and start it, and the second choice, the second correct base pair may not come. So in that case, if the correct thing is coming, you don't get a mutation. The wrong thing is coming and incorporating, they are getting an issue over there. So then that's what I'm to be talking. So we are having the nitrogen master. So it is to be getting and attached to over here. So what it will do, it will be attaching the two bases. So it is to be attaching the two guanine bases. So when it is to be attaching, you can see here a big gap. So this big gap, sometimes three things may happen. Suppose the RNA polymerase, DNA polymerase can do a polymerization reaction and can fill the gap. Sometimes this gap may be filled by the right base pair, right guanine itself. Sometimes it may be going to fill with the wrong base pair. So if it is filling with the wrong base pair, then it may lead to a mutation. Okay, so then we are having the most important alkylating agent, DMS, dimethyl sulfonate, ethyl methane sulfonate, is very very important. Ethyl methane sulfonate, and we are also having the ethyl ethane sulfonate. Okay. So we will be seeing about the EMS or the ethyl methane sulfonate. So what is the very important thing is, EMS has the specificity to remove guanine and cytosine. So if we will be adding these EMS, that is a very beautiful thing about this EMS is, the thing is, it can remove the cytosine or the guanine specifically from the chain. So when this guanine or cytosine is to be removed specifically from the chain, there will be a gap. This gap may be filled up with the correct base. Sometimes it may not be filled up. So if it is filled up with the incorrect base pairs, it may lead to the transition or the transversion. Another example is the methyl nitrosyl guanidine that will add a methyl group to the guanine, cause it to mispair it time and time. So we are also having another method. So what it will do is it will add a methyl group. So if you are adding a methyl group to the guanine, this guanine instead of pairing with the cytosine, it will mispair with the thymine. Okay. After subsequent replication, GC is converted to thymine to adenine and thymine. That is, instead of having the GC base pairing, you will be having the adenine to thymine base pairing. So this is how it is becoming like a equal meeting section to create the. So you can see the base pairing, the drawing has two row and with the cytosine. However, due to the differences in the base pairing property, these EMS that the type is completely changed to ethyl guanine. That will ethyl the guanine will be converted to ethyl guanine. That will be pairing into thymine instead of the cytosine. We are also having the methyl nitrogen. So, okay, you can see here also the entire base pairing is to be different. Guanine has to pair with the cytosine. However, methyl guanine it has become methyl guanine is to be pairing with the thymine. And here the thymine has to pair with the adenine. However, it has become methylamine, and it is to be pairing with the guanine. And we will go to the physical mutants. Okay, so the very important physical mutations are the radiations. We are in our lab also we are doing it's having the 254 nanometers. What is to be telling is below the wavelength range of 340 and photo energy level above 1 electron. So if it is to be having all these things that is below 340 and the photo energy level above 1 electron, you can call it as the mutation, radiation mutation. So what are they? They consist of the UV rays, X-rays, alpha rays, gamma rays, cosmic rays, neutrons, all these are to be. Okay, so the good example is the UV and the gamma radiation. So radiations will exert its mutagenic effect either directly or by creating free radicals. So the free radicals normally cancer and so like that. It's also due to the mutation. So they will cause the free radicals. So these free radicals, radiation free radicals can lead to the formation of bonds between the nitrogenous bases in the. So what it will do is free radical formation will lead to the formation of bonds between the nitrogens. So that what it will do, so if there is a small nuke and what it will do, the thymine will pair with thymine or adenine will pair with adenine. So for a good example is the exposure to the UV light. So it will result in the formation of a covalent bond between the two adjacent thymine. So the thymine has to pair with adenine. So instead of pairing with adenine, the thymine will itself pair along with the thymine. So it will produce a thymine dimer. So if it's not required, the dimer prevents the formation of the double helix at the point where it happens. So it will not allow the replication to proceed further. It's not to be required. So it is what I am to be talking about here. So we are having the free radical formation. So it will lead to the formation of the thymine dimer. So what are the significance of the mutation? So okay, the mutation will help in the identification of the function of a gene. So if you have to be removing a particular gene to a particular nucleotide, that means the gene will may become inactive. So a particular protein will not be expressed. So it will lead to help in the identifying the function of a particular. Again, the thing is it is used in a desired region to create a suitable mutant to produce vaccine. So if you want to have vaccines and all, so we can create the mutant. We can disable a particular vaccine protein and we can use it as a vaccine. Then the spontaneous mutation are very important. because of the bacterial perspective, because they were the ones who induce the antibiotic resistance in bacteria. So how a bacteria is to be getting resistance to a particular antibiotic is with the help of this mutation. So the mutation can also change in the phenotype, such as the appearance of the antigen, alteration in the physiological property, change in the colony morphology, nutrition requirement, biochemical reaction, growth characters, virulence, strength. So all these changes, okay, the surface antigenic property may differ, physiological properties may differ, the colony morphology, sometimes the red color colony is a colorless colony because due to the deficiency of a particular gene, their nutrient requirement may also differ. Maybe they may be not be able to synthesize a particular amino acid or a particular vitamin. So we need to supplement them. Then the biochemical reactions, the biochemical reactions may change, the virulence may change, the host may also change. This today we will be finishing the today's class. So just to go through the different things. Just to finish. So first thing is we will explain about the two methods. One is a point mutation. Okay, first the point mutation means it is just removing one, two nucleotides. So it may lead to the silent mutation by which you will be not be observing any change. Or the nonsense mutation means it will be completely stopping the particular protein. Or we also getting the missense mutation. That is, instead of a particular amino acid, we are getting a different amino acid. And we also studied then we also studied about the translation and the translation. It is between purine or between the pyrimidic, you can call it as a transition. Or if it is taken in, a, in a crossed manner, it is between purine and pyrimidine or between pyrimidine and purine, you can call it as a translation mutation. Next one is we also seen about the chromosomal mutation. We have seen about the deletion, by which a great region of chromosome has been deleted. So it may be fatal. Good example is the Friedreich syndrome. We also seen about the duplication. One region is to be copied one more time. And it will not be very problematic until it lands on the non-coding region. Next one is the inversion. So inversion will also will not lead to any abnormalities unless it is to be balanced with some of the extra DNA. Okay, next one is we have seen about the alkylating agents. So that will cause a deep urination. So here we are getting the gap due to this joint of the base analogs. So this alkylating agents, that is the alkyl group. Next one is we have studied about the EMS, how it can do the changing. So this EMS can convert the guanine to methyl guanine. So what is the fun over here is guanine has to pair with any cytosine. However, this ethyl guanine is pairing with the thymine. We have also seen about the physical mutation by which this X-rays and the gamma rays and the mutagenic ones. We have also seen about the formation of the thymine. With this, I am completing today's class. If you have any doubts, kindly mail.